Now that we've seen the spring mass system and a little bit of periods and oscillations, let's actually try our hand at an example. So the example we're going to use is just our classic spring mass. Yes, I am using the same picture again. But what we want to do is, if we're given a spring constant, how stiff the spring is, 0.1 newtons per meter, and we know that its oscillation is represented in this picture, so we're going to actually take this animation to be a real picture. How heavy of a mass is connected? So how heavy is this orange block? So first thing we need to do is figure out what is its period of oscillation. Well, the period of oscillation for this thing is about 1 second, and you can time it if you want, but let's just say 1 second for sake of this example. So 1 second period takes 1 second to complete a full cycle or a period. So we say t is equal to 1 second. We also know the relationship between the angular frequency and the period of oscillation. So the angular frequency is equal to 2 pi over the period. So if we figure out that with the 1 second period, multiply this thing through, we get that the angular frequency, how many radians per second does it go through? And it goes through 6.28 radians per second, or 6.28 hertz. So we know the angular frequency, we know the period. We need to know how to relate the angular frequency to something else. And something else is going to be that factor that we've seen before. It's come up again and again. Is this k over m. And that's the angular frequency squared is equal to k over m. This is for a spring mass system. So we're going to rearrange this, and we slide the m to the other side. We divide by omega squared. We get m is equal to k over omega squared as what the mass is. So the mass of this oscillator, this guy over here, is equal to k over omega squared. So we substitute everything in, and we get that mass is equal to 0.1 newtons per meter divided by the 6.28 hertz quantity squared, and we get that that's about 0.0025 kilograms, or about 2.5 grams. So we could look at this from a graphical point of view and come up with about the same equations, and we could see that substituting in this square root of k over m for omega into our period, we could see that the period would start at some max, go to a minimum, go to a max, rearrange that equation, that cosine of omega t in, and solve again, and we would get the same value. But just a simple problem of how to get a period, or using a period and using a spring constant, we can figure out the mass. Kind of an interesting note is actually, this is how one of the methods for weighing an astronaut in space. You can't really figure out its mass or its weight, because a weight is proportional to gravity, but you can figure out how heavy or how much mass an astronaut has based off of how much they oscillate. So they have a wonderful little chair that they stick astronauts in, and they vibrate them, and they figure out how long it takes to take a period, and then they can figure out the astronaut's mass based off of it. So good luck with the rest of these slides in the learning module, and hopefully oscillations are starting to slowly build up to be a little bit more of a clear picture for you.